Okay, I'm going to do 194, which is about Fourier series. It's a nice little question, this one, but the truth is that you're being asked to do something that realistically, is a touch on the difficult side. So it's not a realistic thing you've got to worry about, for example, being in the exam or anything like that. But it's interesting, and it's really, really important. So the question is to show that the infinite set, which is given by just a constant, and then sine and cos x with different periods, that these form an orthonormal set in the vector space of continuous functions on the interval from 0 to 2 pi. Now, in fact, they form a basis on this set, in this vector space, which is really fundamentally important and useful. But that requires analysis, and what we're trying to do here is just show that they're orthonormal. They're an orthonormal set. So the inner product we're given is the inner product of f with g, and you could just write this as the inner product of some function of x and g of x. It's the same thing, and that's just equal to the integral from 0 to 2 pi of f of x and g of x. Okay, so what we have to do is we'd have to show that for each of these functions that the inner product of those functions with themselves is 1. So in other words, that means that their length is 1, and the inner product of any two distinct functions is 0. Now what this comes down to, basically, is the fact that we can represent these functions in terms of the exponential function. So in particular, we use the fact that e to the ix is equal to cos x plus I sine x. Alright, and so that tells us that cos x is equal to 1 over 2 e to the ix plus e to the minus ix, and sine of x is equal to 1 over 2i times e to the ix minus e to the minus ix. So this observation makes everything very simple. And the final thing you need to know is that the integral from 0 to 2 pi of e to the I nx dx. So if n is equal to 0, then this is just the integral of a constant of 1, and this is 2 pi for n equal to 0. But if n is not equal to 0, then this is equal to, it's the exponential, so it's just equal to the integral, that's equal e to the I nx over I times n, evaluated at 2 pi and 0. So e to the 2 pi I times n is equal to 1, because it's just an integer multiple of 2 pi. Likewise, e to the I times 0 is also equal to 1, and so this thing here is just equal to 0. So obviously for n being an integer, I should explain, okay? So this is only true, this relationship is true when n is an integer. When n is 0, then this integral is just 2 pi. When it's another integer which is not 0, then this integral is 0. And so how does this help us? Well, all of these integrals, all of these inner products that we're interested in can be written in this way. So again, I'm not going to go ahead and do all of them, alright? But let's look at the inner product of 1 over root 2 pi with itself. Okay, so that's just equal to the integral from 0 to 2 pi of 1 over root 2 pi dx. In other words, this is equal to 1 over 2 pi times the integral of 1 from 0 to 2 pi. That's equal to 1. Let's have a look at the integral. So I'm not going to do all of them. What you need to do, in fact, is do any possible combination. So 1 over root 2 pi with itself, 1 over root 2 pi with 1 over root pi sine of nx, also with 1 over root pi cos of nx, etc. You have to look at all possible combinations, and then you have to look at the integral of 1 over root pi sine of nx with 1 over root pi sine of nx, which is what I'm going to do next. So this is when the two constants are equal. Okay, let's have a look. So this is equal to 1 over pi, integral from 0 to 2 pi, and here I'm just going to substitute the expression for nx. So this is 1 over 2i e to the I nx, take e to the minus I nx, and then times 1 over 2i e to the I nx minus e to the minus I nx dx. Okay, now let's look at what terms we get when we expand this. So e to the I nx times e to the I nx gives us e to the 2i times 2nx, and the integral of that's going to go to 0. When I take the cross terms, I'm going to get e to the minus I nx times e to the I nx, and that gives us e to the 0. So in other words, it's a constant term. And then I'm going to get the same thing. So this cross term and this cross term will give us 2 of those, and those are going to be 2 constants. So it's just 2 from those 2 terms, so minus 2 rather. And finally, from minus e to the minus I nx times minus e to the minus nx, that'll give us e to the minus I 2nx, and the integral of that's going to be 0. So this is just equal to 1 over pi, integral from 0 to 2 pi. Now 1 over 2i times 1 over 2i gives us minus a quarter, and then we've got minus 2 from e to the 2 terms of e to the I nx times e to the minus I nx, and we integrate that. And then we evaluate this, so this is just equal to a half, so it's 1 over 2 pi integral from 0 to 2 pi of 1, and that's equal to 1. Okay, so sine nx is the length of sine of 1 over root pi sine nx is 1. And the last one I'm going to do is to show that the integral of 1 over root pi sine nx and 1 over root pi sine mx is equal to 0 when m is not equal to n. So this is equal to, again, 1 over pi integral from 0 to 2 pi, and this time we've got 1 over 2i e to the I nx, take e to the minus I nx, and 1 over 2i e to the I mx, take e to the minus I mx dx. And now if you look at this, when I expand it out, I get e to the I nx times e to the I mx, so that's m plus n. That's not 0, so the integral which corresponds to that is 0. I get e to the I nx times e to the minus I mx, so I get n minus m. That's also not 0, and so that integral is also 0. Then I get minus m minus n plus m, also not 0, so we're showing that this is 0, showing that that's 0, finally this is 0, and that gives us minus m minus n, take m, that's also 0, and so the whole thing has to be 0. Okay, now you've got only a couple more integrals to go. You've got to do the same trick for cos of nx, but in the end what you'll see is that the length of each of these vectors is 1 with respect to this inner product, and that they're all orthogonal, and that makes this an orthonormal set. And yeah, it's a really nice problem and just tremendously useful. But I'll leave it there.